Hello. So, first of all, I'd like to apologize for the difference between the titles because on the website you might see it as cosine similarity preserving compression of dense embedding vectors, but we'll be dealing with dimensionality reduction. So, well, here we are, the cosine similarity preserving dimensionality reduction of dense embedding vectors. So I am Witold Wydmański. I am assistant at Małopolska. Oh, okay. I am Witold Wydmański. I am assistant at Małopolska Center of Biotechnology and a computer science student at Jagiellonian University. My research topics are mainly focused on NLP and information mining, but I also research algorithms for metagenomic analysis and general tabular learning. So, well, yesterday during the keynote speech, Dr. Berger-Wolf mentioned the problem of tracking animals. And the problem that she was talking about is a great example of the exact mining, because if we take a photo, if we have a photo of a giraffe, and we say that on the photo we have Jeffrey the giraffe, and actually it is Gordon the giraffe, then it doesn't matter that they look very alike and that they are cousins. We made a mistake. Those are not the giraffe that we are meant to find. And, well, we were just wrong. But fortunately, in text mining, the case isn't so simple because we can be more or less wrong. And so, for example, if we have some text description of an animal and we detect from the text an animal that is not precisely the one that the description was about, but we are close, then there are many metrics that can tell us how close we were. For example, a commonly used one is the WordNet distance. So we try to find how far away are we in the hierarchy between the words that between the concept that we were meant to find and between the concept that we actually found. And recently, thanks to the rise of large language models, we are moving more and more towards the text embedding distances. So we no longer depend on some arbitrarily created hierarchy of concepts, but we can actually use a learnable difference thanks to the embedding space. And one of the most commonly used differences is, of course, the cosine distance. And, well, if we try to use this framework, so what we can do is we can vectorize some sentences and just assume or just check how close semantically they are to each other by comparing the angle of the vectors that we have received, what we have obtained. So there are a lot of problems actually from this approach. I mean, it isn't a straight up upgrade in every dimension that we could have found. So the problem is that handling embeddings is problematic because vector comparison is slow and it requires a lot of storage for indexing the embeddings. And our database's usefulness is proportional to its size. And so are the processing costs. And I don't mean costs in the terms of monetary costs, but also the time. So the more embeddings, the more vectors we have, the more comparisons we do, the slower is our querying. And of course, there are a lot of methods of mitigating the problems, like, for example, the approximate nearest neighbors algorithms, but they aren't enough because, well, they allow us to avoid doing comparisons. But in the end of the day, we still have to compare the vectors. And well, what you can see on the left is t-SNE projection of embeddings of some PubMed publications. So I love the clusters that they are making. And well, the obvious solution to this problem will be to just scale down the vectors, because as you have seen on the cosine similarity equation is, of course, the number of computations that we have to do is proportional to the vector length. So the shorter they are, the less computation we have to do. However, how can we do that so that we preserve the cosine distance? Because, okay, if you want to retrain the whole model, then of course we can just add another layer at the end that will be shorter than the original layer, and we can just go on like this. But the problem arises when we don't have enough data to train the whole model, or maybe we don't have access to the whole model. So once we have the already processed sentences on already vectorized concepts, how can we proceed then? What can we do to scale them down? The second question is, what do we lose in doing that? Because, well, as a wise person once said, there ain't no such thing as a free lunch. So we cannot just gain speed without losing anything. And we have to measure how much we lose. And finally, what should be the exact procedure of scaling the vectors? So for the rest of the remainder of the presentation, I'll be telling you about the datasets that we've been using, the metrics that we used to measure our progress. I'll also define the framework for the dimensionality reduction and tell you about the algorithms that we have tested and that either failed or didn't meet our expectations. And then in the results, we'll not only focus on the performance on the datasets, but we also talk a bit about the generalizability of the methods. So let's dive into the methods then. The datasets that we have been using, there were two of them. The first one was the Microsoft markup for semantic similarity, and the second one was PubMed or Medline database for information retrieval. For the MS markup, the matrix was simple. So the MS markup dataset is formed as a set of triplets. So the first element of each triplet is an anchor or a query. So it is a word or a short sentence. The second part of each triplet is a positive sample. So it is a text that is relevant to the query. And the third one, the negative sample, is, well, irrelevant. And our metrics for this dataset is the number of triplets in which the embedding of the positive sample is closer to the anchor than the embedding of the negative sample. As for the problem of information retrieval in PubMed, it isn't so simple because the dataset that we are using is kind of fast. Okay, we have been using a scaled down version, so not all 30 million publications, but only 100,000. But still, it is a non-trivial amount of publications that we cannot just, a person that is looking for information cannot just go through all of the 100,000. So the way that the problem is framed is that each publication in the dataset can be either relevant or irrelevant to one of the 70 queries that we tested it on. And in order to check in order to keep it as close to real life as possible, the PubMed dataset was deployed on an Elasticsearch cluster with 3 nodes. And the metrics that we're using are the recall and mean average precision. So of course, the recall is the number of relevant publications that our algorithm have chosen as relevant. And mean average precision can be seen as, well, the average precision at seen relevant documents. So basically, those metrics complement each other, and that the recall gives us points if we find relevant documents, and mean average precision penalizes us for incorrect ranking of the articles. And the reduction framework that we have chosen, it was that we first we transform the sentence into an embedding vector v, and then we reshape the vector v into n vectors of d dimensions. And then the reduction operation was done on each of the reshaped vectors separately. So, and well, then finally, the resulting vectors were concatenated into the final reduced vector v'. And the algorithms that we had evaluated, there were a lot of, most of them were the classical ones. So the PCA, the locally linear embedding, the whitening transformation, and UMAP. And also, there is a mistake. Averaging is not trainable, but whitening is trainable. So those check and X should have been switched. But well, yeah, averaging is not a trainable operation because we just take the d-dimensional vector and we average its elements into a single scalar. Autoencoder network is, well, a simple one layer neural network that takes the vector v, compresses it into v', and then tries to expand it so that the cosine similarity between the original and expanded vector is as close as possible. And the Siamese network is also a commonly used setting in which, and this is the only supervised algorithm of the bunch. So we take the triplets from the MS Marco dataset and we train the network so that the dimensionality reduced embedding of anchor is closer to the positive sample than to the negative. And also we added a recent idea from a paper. Unfortunately, I cannot remember its name right now. But the idea is using a variance loss so that the embeddings inside a single batch aren't optimally of a variance equaling 1. So that, well, it basically it helps us to avoid embedding collapse so that the embeddings don't end up in a single place. And as for the results, well, the abstract on the website said that we managed to keep to 96% of the original accuracy with 8 times reduction, but we improved it to 98% of the original accuracy. So what you see here is the table and, well, a graph visualizing the table, which is a function of percentage of original accuracy for different reduction rates. So for example, the bolded one for the PCA, 98.1%, means that if we reduce the vector, the size of the vector 8 times, we are still able to retain 98.1% of the original accuracy. So we can scale down the vector from 668 dimensions to, okay, I won't be able to do the math in the head, but for example, the 24 reduction rate means that we are able to scale down from 768 dimensions, sorry, to 32 dimensions and still retain 94.2% of the original accuracy using the Siamese network algorithm. So, well, as you can see from the table and from the graph, there are 2 winners. The first, for the smaller reductions, there is a PCA, which is performing, well, better than at least I expected. And then for the larger reduction rates, it gets overtaken by the Siamese network. And also, well, the simple averaging also does pretty well consistently. So what you can see here on the graph on the left, it is a linear scale. It shows the degradation of the performance of the embeddings in the linear scale. So you can see that first it diminishes quickly, and well, basically after we cross the 24 times reduction, it slows down, but also the results are getting pretty bad. And as for the ranking of the methods, the three winners so far is the PCA algorithm, the Siamese network, and simple averaging. So those are the three algorithms that we chose to further benchmark on the PubMed dataset. And as for the PubMed, well, first let's talk about the performance of the server. So you can see that all of those graphs are elbow-shaped, and we stop gaining anything after going down to the 24 times reduction. But at the 24 times reduction, we managed to cut down the indexing time down to 1/3. We speed up the query time by 5 times, and the storage is lower than 20% of the original. And the numerical performance is a bit worse than on the MS Marco dataset, but the trend is here. So the Siamese network is first underperforming the PCA, but then is getting better. So all the evaluations that we have done so far were done using the all MPNet based model. And for the test of generalizability, we chose the BioBERT, the sentence similarity fine-tuned BioBERT, because those two are very different models in the term that even their training regime is completely different. And what is interesting is that apparently the SBioBERT wasn't fully trained, because once we applied the Siamese networks, we actually got better, both in the terms of accuracy and recall. But this is a quirk of a model, not of the method, so we normalized it to just stick to the looking at the trend. But let's keep in mind that you can see, even though on the graph the Siamese network underperforms for the BioBERT model, actually it, in the terms of pure performance, it was better, but it started diminishing quicker. So as for the final recommendations, it looks like we can safely reduce the dimensionality by 4 times without losing any, okay, maybe not any noticeable points, but without losing too much points. So, and if we want to go further, we can use the Siamese network to, well, pretty much go as low as we want to, but we have to keep in mind that the embeddings will start getting pretty much useless quickly. So, thank you, and I invite you to ask questions.
We could have time for one quick question, if there's any. So I have a quick question. So certainly this is very interesting, and to me it's very useful because we work with PubMed scale data on a daily basis. So in your experiment, you started with you said 100,000. Do you think that can be applied to millions of 34 millions of PubMed data?
Yes, I think so. Well, the origin of the study was that we actually weren't able to fit all the data that we needed into our cloud, because even though we could vectorize the whole publications if we were using a single vector per publication, if we wanted to increase the resolution, then, well, we came into the wall of performance and storage. So this is exactly what we are hoping to do. We are hoping to do further experiments on the whole 30 or 40 million articles.